Welcome to Brigham Young University. We're grateful to gather with you here on campus today. My name is Grant Jensen. I'm the Dean of the College of Computational, Mathematical, and Physical Sciences. I'd like to extend a warm welcome to our speaker today, Nobel Laureate Kip Thorne. I'd also like to recognize some guests with us today, Elder Quentin L. Cook of the Quorum of the 12 Apostles and his wife Mary Cook, Elder Garrett G. Gong of the Quorum of the 12 Apostles, Elder Clark G. Gilbert, Commissioner of the Church Educational System, C. Shane Reese, President of Brigham Young University, and his wife Wendy Reese, and many other members of the administration. Thank you all for joining us. At BYU, we seek to learn all truth through both spiritual and scientific approaches. In the scientific approach, we do experiments to learn about the world around us and beyond. An important part of that process is that we build upon all that has been done by scientists and mentors who came before us. Isaac Newton once said, "If I have seen further than others, it is by standing on the shoulders of giants." Students, you will make discoveries and build new technologies that we can't even imagine today. And in preparation, you should dig deep and learn all you can while you're here at BYU. Today, we're grateful for the opportunity to dive deep into the field of gravitational wave physics with Nobel Laureate Kip Thorne. When I was a kid growing up in Los Alamos, New Mexico, I thought everybody was a physicist. And then I got a little older and realized not everybody was a physicist, but everybody wanted to be a physicist. Today, you're proving that true. No matter what discipline you come from, we're glad to have you with us to learn some physics today. As is customary at BYU, we'll begin this lecture with an opening prayer by Nate Gary, an undergraduate physics student from Centerville, Utah. Nate.
Our dear Heavenly Father, we are so grateful to be gathered here together today as a campus community and as other friends to hear from Dr. Kip Thorne about his experiences and research in gravitational wave astronomy. We're grateful for the opportunity we have to learn in many different capacities at this university, and we're grateful for the community we have. Please help us to have our minds open to be enlightened as we listen today, and please help us to always strive to be more like Thee. And we say these things humbly in the name of Jesus Christ. Amen.
Dr. Thorne was born in 1940 in Logan, Utah, and is currently the Feynman Professor of Theoretical Physics Emeritus at the California Institute of Technology, commonly referred to as Caltech. He received his BS in physics in 1962 from Caltech and his PhD from Princeton University in 1965, then returned to Caltech on the professorial faculty in 1967. At Caltech, Dr. Thorne led a research group working in relativistic astrophysics and gravitational physics, with emphasis on relativistic stars, black holes, the theory of time travel, and especially gravitational waves. 53 students received their PhDs under his mentorship, and he mentored roughly 60 postdoctoral students. He co-authored the textbooks Gravitation and Modern Classical Physics, and was sole author of Black Holes and Time Warps, Einstein's Outrageous Legacy. Thorne was co-founder with Rainer Weiss and Ronald Drever of the LIGO project that stands for the Laser Interferometer Gravitational Wave Observatory, which I'm sure Dr. Corn will be telling us more about. In the hands of a younger generation of physicists, it made the breakthrough discovery of gravitational waves arriving at Earth from the distant universe on September 14th, 2015. For his contributions to LIGO and to gravitational wave research, Kip shared with Weiss and LIGO director Barry Barish the 2017 Nobel Prize in Physics and several other major awards. In 2009, Dr. Thorne stepped down from his Caltech professorship to ramp up a new career at the interface between art and science. This has included being the lead scientific consultant on Christopher Nolan's blockbuster movie Interstellar, which I bet a lot of you have seen, and a book titled Warped Side of Our Universe, comprised of paintings by the artist Leah Halloran and poetic prose by Kip Thorne himself. Before Dr. Thorne speaks to us, we'll now enjoy a personal introduction by his childhood friend, Elder Quentin Cook of the Quorum of the 12 Apostles of the Church of Jesus Christ of Latter-day Saints.
My purpose is to describe my friend, Kip, from a personal perspective. We both grew up in Logan, Utah, attended junior high and high school together. That is, of course, before he became an acclaimed American theoretical physicist, renowned for his groundbreaking work in gravitational physics and astrophysics. Even in his youth, he was off the map academically, especially in the sciences. His parents were both professors at Utah State University. His father was also a senior administrator. It is of significance today that his marvelous mother, Allison Comish Thorne, was a graduate of Brigham Young University. Both parents had great influence on Kip, but I love one account that demonstrates this. Kip, when he was 8 years old, with his mother helping, using chalk, mapped out the solar system to scale, placing the sun at the intersection in front of their house. They then placed the other planets throughout Logan and North Logan according to their distance from the sun. She was an amazing mother. I first became friends with Kip when we sat side by side in 8th grade Latin. It was interesting and entertaining. The teacher loved to throw pop quizzes. We became aware of the fact that she usually wore a lovely purple dress on the days that she had a pop quiz. We think she thought she was Caesar. We did like her, though, and became good friends. Our senior year, Kip became the editor of the Logan High 1958 yearbook titled Amphion. I'm showing it here. He both wrote the text and took many photos. It was a labor of love, and Kip did a spectacular job. He underemphasized his position as editor and included all who helped. That was classic Kip Thorne. He never tried to take credit for anything, even when he won the Nobel Prize in physics. In our junior and senior years, we had a particularly close relationship representing Logan High in debate tournaments. We all became close friends. Kip's debate partner was Merlin Olson, who was even in his senior year in high school, had achieved All-American status in football. He subsequently became an All-Pro tackle for the Los Angeles Rams 14 times. The judges might have given them some victory just because they were afraid of Merlin, I don't know. Kip, Merlin may have had your back in debate, but he had my back in football. Merlin played left tackle, and I was quarterback, and I seldom got hit. Although the title did not exist then for high school scholars, Kip achieved All-American status in science subjects. What is even more important is that Kip is and always has been one of the kindest, warmest, and most ethical people with whom I have had the opportunity to associate. In addition, he has a great sense of humor. It is my pleasure to introduce my dear friend, Dr. Kip S. Thorne. Kip, we are extremely grateful to have you be here and to make this presentation.
It's a great honor to be here and a real pleasure. I have had fascinating conversations with students especially, but also faculty today. And some of the best questions I've ever been asked came from the students here at BYU. I was born in and grew up in Logan, Utah in the 1940s and early 1950s. As a child, my great ambition was to be a snowplow driver because that was obviously the most powerful job in the world, until my mother took me to a lecture about the solar system. And Quentin has told part of that story. I was just enchanted by the enormous distances between the planets and the very small size of the planets compared to those distances, which I learned from my mother in the little project that we did together that Quentin described. And so in 1948, at age 8, I abandoned snowplow driving, decided I wanted to be an astronomer. This is me at age 13 with my mother, Allison Thorne, and my 4 siblings. And it was at age 13 that in a used bookstore here in Salt Lake City, I discovered a book titled 1, 2, 3 Infinity by George Gamow, who was a professor at the University of Colorado, a Russian emigre, a very eminent cosmologist. And in this book, I learned that there are laws of physics that govern the universe, control how the universe evolves. And among those was Einstein's relativity laws, which say that space and time are warped, and that warpage somehow gives rise to the gravity that holds us to the surface of the Earth. I was just totally enchanted with this idea of the laws of physics and Einstein's relativity. So I abandoned astronomy, decided I would be a physicist who worked on astronomical topics, and so here I am. And I don't know any others among my friends who made the decision to go into science like this so early, but it really was due to my mother, to whom I'm forever grateful. And thus it was that in 1962, upon graduating from Caltech as an undergraduate, I went to Princeton University for graduate school to work with John Wheeler, because John Wheeler was the greatest guru, mentor on relativity theory at that time. And from Wheeler, I learned that there is what nowadays I call the warped side of our universe, objects and phenomena that are made entirely or largely from warped space and time. Examples that I will touch on during this talk are black holes, neutron stars, the Big Bang in which our universe was born, we believe, and gravitational waves. Now, a black hole then is made from warped space-time, and one aspect of that is that the circumference of this black hole is much smaller than its diameter. The black hole, if you were to look at it, it would look like a bowling ball, an absolutely black, dark sphere. And obviously a bowling ball has a circumference that's much bigger than its diameter, but that's not the case here. And how is that possible? A simple analogy answers that question. Let's take a child's trampoline, a sheet of rubber up on tall stilts, and let's put a rock at the center of the trampoline so the rubber bends down in that manner. And let's suppose that you're an ant. But you're a blind ant, so you can't see what's going on here about the rubber and the three-dimensional universe out here. But you go about measuring the diameter around this region by marching around, or the circumference, and you measure the circumference, and then you measure the diameter, and it's a very, very, very large diameter. And having studied physics at BYU, you say, well, obviously, my universe is warped. And it must be warped. There must be some higher dimensional universe in which it's warped. And that, of course, you're quite right. Well, precisely the same diagram explains a black hole. I take a black hole and I take a two-dimensional surface through the center, an equatorial slice through the black hole, and I look only at that. So I just ignore the third dimension of our universe. But then that has a diameter that is far larger than the circumference for precisely the same reason, because our universe can be thought of as embedded in a higher dimensional universe, which is called the bulk, or in the movie Interstellar, it's called the fifth dimension. The three space dimensions are familiar. Time is the fourth dimension, and this is the fifth dimension in Interstellar. But this space is warped in this higher dimensional bulk in the same way as my analogy with the rubber sheet. As seen from the bulk, then, a black hole looks like a funnel, and I'll refer back to that later in the lecture. Our universe is a funnel in the bulk, in the higher dimension. Now, the thing that we all are familiar about black holes is if you fall into one, you can't get out and you can't send signal out. And so here I am falling into a black hole. I've removed one space dimension, of course, and so I'm falling down this surface, which is part of our universe. The bulk is the third dimension here. And I'm transmitting microwave signals to you with a little microwave antenna. And when I pass through what is called the horizon, which is the surface of the black hole, or the event horizon, thereafter, I and the microwave signals get pulled willy-nilly down into the thing that's at the center, which was a rock in my analogy. Now for a black hole, it's called a singularity. It's a region where the laws of physics as we know them fail and get replaced by new laws that we don't understand very well, called the laws of quantum gravity. It's a place where space is enormously warped, extremely highly warped. And we get pulled down into the singularity. Now, not only is space warped, so is time, so that if I go down and I hover just above the horizon of the black hole, then time slows enormously compared to time back here on Earth. If I hover right at the horizon, then time slows to a halt. And beneath the horizon, time flows in a direction you would have thought was a space direction down toward the singularity. And that's another reason nothing can get out of a black hole, because nothing can move against the local forward flow of time. If it's possible to go backward and do backward time travel, it's only by going out into the universe and returning before you started. You can't move against the local forward flow of time. There's a third aspect to the warping of space-time. That's a whirl of space. If the black hole is spinning, then it drags space into a whirling motion around itself, fast near the horizon, much more slowly farther away. And so this, in fact, now I'm showing you, before this was just my hand drawings to give the basic idea. But for a fast-spinning black hole, this is a precise depiction of the warping of space in the bulk. The color coding is the slowing of time, so where it's yellow, time is flowing at 10% of the rate of flow of time back on Earth. And the angular velocity of whirl of space is proportional to the white arrows. Now, what warps the black hole space and time? The answer is the energy contained in the warping. If you imagine taking that sheet of rubber and you push with your fist, you have to put energy into that rubber to stretch it. And so the warping of space and time has energy, and that energy produces the warping. The black hole is held together by what we call a nonlinear self-interaction. It was Albert Einstein then who formulated the laws of general relativity about warped space-time in 1915, and the following year in 1916 he used those laws to predict the existence of gravitational waves. And so if I have a gravitational wave that's propagating into the screen, and I put the screen up in interstellar space, and I actually forget the screen, let's just put an array of particles that are all at rest with respect to each other in interstellar space. Then when a gravitational wave comes along, with each of these particles moving inertially, moving under its own inertia, as the gravitational wave comes along, it stretches space horizontally and squeezes it vertically, perpendicular to the direction of propagation of the wave. And so it is a stretch and squeeze of that sort. And that's the character of a gravitational wave as predicted by Einstein's relativity laws. Now, there are only two types of waves that can be created in the distant universe and travel to Earth, bringing us information about what's far away. Electromagnetic waves, that includes light, radio waves, X-rays, gamma rays, and so forth, and gravitational waves. And that's all, as far as we know, from the laws of physics. Now, it was Galileo who built a small optical telescope 400 years ago, pointed it at Jupiter, and discovered Jupiter's 4 largest moons. And in the process, he created instrument-based electromagnetic astronomy. In 1972, together with students and colleagues, I began to develop a vision of a desire to do what Galileo did for gravitational waves, to create gravitational wave astronomy by building some sort of instrument to enable us to measure and observe the gravitational waves as they go by. Now, gravitational waves are made from the same thing as black holes, from warped space-time, so they are the ideal tool for exploring the warped side of our universe. The gravitational waveform is a pattern of stretching a plot vertically and squeezing as time passes. And so this is rather like a sound wave that you put onto an oscilloscope to see the oscillation of the sound wave. And this, just as a sound wave brings you information, so a gravitational waveform carries information. It's like a symphony's sound tickling your eardrum, bringing you information, in the case of sound, information about the instruments that are playing in the orchestra. Now, part of our vision for electromagnetic astronomy was based on the enormous contrast between electromagnetic waves and gravitational waves. Electromagnetic waves are oscillations of the electric and magnetic fields traveling through space as time passes. Gravitational waves are oscillations of the very fabric of space-time itself, oscillations of the shape of space and the rate of flow of time. Gravitational waves are emitted by oscillating electrically charged particles. Gravitational waves are emitted by oscillating massive bodies or by the dynamical oscillations of warped space-time, in the case, say, that black holes collide, that I'll describe in a little while. Electromagnetic waves are all too easily absorbed and scattered by the matter that is between us and their source. Gravitational waves are never significantly absorbed or scattered, even if they're created in the Big Bang birth of our universe and travel to Earth from then, where the universe in its very early phase is extremely hot and dense. They just travel right through that hot, dense matter, unscathed by absorption and scattering. If you think about these enormous differences, it becomes pretty obvious that after a bit that many gravitational wave sources will not be seen electromagnetically. And so surprises are likely. Our knowledge of the universe today is based on electromagnetic observations. We're going to be seeing things that are radically different that you don't see electromagnetically, so surprises are likely. So this was our vision, and it was in that same year, 1972, that Ray Weiss, whom I had known at Princeton when he was a postdoc and I was a graduate student at Princeton, he sent around to me and his other colleagues a manuscript in which he described an idea for a detector for gravitational waves that came to be called a gravitational wave interferometer. The basic idea of this detector is that you hang 4 mirrors from overhead supports like this, 2 along each arm of an L-shaped configuration. And when the gravitational wave comes along, it pushes these mirrors apart because it's expanding the space between them, pushes these together, and then the next half cycle pushes these apart and pushes those together. And if you, but this is a tiny, tiny motion, as I'll describe in a moment. And if you then arrange it so that the round-trip travel time in here is an integral number of periods of the electromagnetic waves of the light in this laser beam here, and you use a laser then to send laser light in through a beam splitter, and then it goes in between these mirrors. If the travel time is an integral number of periods of the electromagnetic wave, then the light gets trapped in here and can bounce back and forth hundreds of times between those mirrors. And so light comes through the beam splitter, it gets split in two, gets trapped in here for hundreds of round trips, while this alarm is long and hundreds of round trips while that alarm is short. Then it comes back and it interferes. And as the arms oscillate, the interference between those two waves that are coming from the two arms with stretching and squeezing arms produces an intensity going to this photodetector that rises and falls in proportion to the stretch and squeeze of the gravitational wave. So just the rising and falling intensity maps out this gravitational waveform. So that was his idea. I looked at the numbers in his manuscript, and I thought about it for a short time. And I was about to send off to the publisher the manuscript of what turned out to be a very influential textbook on relativity called Gravitation by John Wheeler, myself, and Charles Misner. And just at the last minute, before the manuscript went to the publisher, I stuck into the manuscript a brief description of Ray Weiss's idea, and then an exercise for the student to show that this is not very promising. I ate crow after that. But let me explain why I thought it was not very promising. Take 1 centimeter, divide it by 100, you get the thickness for human hair. Divide by 100, you get the wavelength of light that is used in this. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100, you get the magnitude of the mirror motions that I expected would be produced by the strongest gravitational wave sources we would ever see if the distance between these mirrors was a few kilometers. That's 10 million times smaller than the diameter of the atoms of which the mirror is made. And to think you could do this kind of interferometry at a scale is 10 million times smaller than the individual atoms, it's just incredible to me. But then I studied Ray's paper. I talked in great depth with him and with Vladimir Braginsky, a colleague in Moscow, Russia, who was, these were the two experimenters I most respected. And I gradually came to be convinced that we had a real possibility of success. And so I committed myself that I and my students would devote much of the rest of my career and much of their careers to helping the experimenters pull this off if they chose to move forward with it. And so it was in 1978 that we created at Caltech an experimental gravity research group to work on this kind of gravity wave detector, led by Ronald Drever, whom we imported from Glasgow, Scotland. We brought Drever in because he was very creative, and this was so difficult. We needed somebody highly creative to invent ideas for improvements on Ray's idea. And he made some significant improvements on Ray Weiss's design. And then from 1978 to 1989, there was effort, very hard effort, on building and running prototype gravity wave detectors with sizes of a few meters up to 40 meters at Caltech, at MIT, in Glasgow, Scotland, where Ron Drever came from, and in Garching, Germany, with a lot of interaction as well as competition between these research groups. And there was major progress made by 1989 in reducing noise. And so with the progress, obviously really major, in the late 1980s, we created a collaboration between Caltech and MIT called the LIGO Project for Laser Interferometer Gravitational Wave Observatory. And we brought in Robbie Vogt, who had been the chief scientist at JPL. In fact, he created the job of chief scientist. And he had then been involved in big science like this, but in the space program, to lead us in writing a construction proposal and submitting it to the U.S. National Science Foundation for actually doing the final design and the construction of 4-kilometer-long interferometers, gravity wave interferometers with arms 4 kilometers long. We said we would do this in 2 steps. We would build initial interferometers that were of a design that we knew how to build at that time. And they would show us the problems that were unexpected problems that might get in the way. They would probably not see any gravitational waves, but they would give us the information we needed to build much more complicated advanced interferometers that should have a reasonable probability of success. This was really a lot of hubris to think that you could pull it off in 2 steps like this, but that was the plan. In 1992, this was actually funded by Congress, and from 1995 to 1999, the facilities to house the interferometers were constructed. And so the interferometers, we built 2 of them, one in Hanford, Washington, that's sort of a desert. This is a corner station in which the laser and the corner mirrors are, and the end mirrors are 4 kilometers away down there. This is Livingston, Louisiana, down there, where the corner station and the mirror is 4 kilometers away. The actual construction was led by Barry Barish. We brought in a different director because Barry had more experience in actually running big projects like this. We needed somebody with maximum amount of experience. And it was Barry who shared the Nobel Prize with me and Ray Weiss. And we also, Barry then expanded LIGO beyond Caltech and MIT to a much larger LIGO scientific collaboration where there are major contributions being made by people from all over the United States, from Canada, from Europe, from India, from Asia, a total of about 1,000 members of the collaboration by the time we finally detected gravitational waves. 2000 to 2015 was a period in which we first built our initial interferometers, just like we had said we were going to do, and installed them, searched for gravity waves, and saw none. When we were halfway through that process, Barry Barish got stolen away from us by the high-energy physicists to lead the design study for the first total worldwide collaboration on a high-energy physics facility called the International Linear Collider. People who had the skill to lead projects like this are very few and far between, and Barry was really the best of them, I think, that we've ever seen. And so we brought in Jay Marks from Berkeley to take over, and he took over admirably well. And then 2010 to 2015, we built and installed the advanced gravity wave interferometers under the leadership of a third director, David Reitze. David was the first director that we had who actually came from inside our collaboration, and David is still the director of LIGO here in 2025. Now, I just want to show you some photos of advanced LIGO to give you some sense of the complexity of this instrument. Here you see the mirror that is hanging from overhead supports. It looks like it's being held tightly by a surrounding structure. That's not the case. It is hanging from a fiber, a fused silica fiber, a quartz fiber, hanging from another cylinder that's up in here that is hanging from a great big plate that is hanging from another plate. So it's 4 cascaded pendula, which is a key thing to making the mirror's motions insensitive as possible to the motion of the ground underneath the mirror. It's called seismic isolation. It's a very complex seismic isolation system. This is the vacuum system in the corner station. The beam splitter and the corner mirrors are off here in the corner, but all of this other stuff is stuff that is required to deal with the enormous numbers of things that might be able to go wrong. I can't begin to explain all of the things in there, except to say there's an enormous number of them. And one way to understand that is that there, in fact, are 100,000 different components in there, plus different points in the environment that could influence this gravity wave detector. And each of those components can be pinged and asked, what were you doing when this purported gravity wave came along, just to be sure that all of the components were behaving properly. But when I was told by the experimenters there were 100,000, I couldn't believe it, but that's really true because of the 100,000 key components. So you get some sense then that these are tremendously complex. Let me now go back in time from 2015 to 1992 to pick up 2 other tracks of this story. In 1992, it was pretty clear, I think, to everybody that the strongest sources of gravitational waves for LIGO would be binary neutron stars. Each neutron star has a diameter of about 20 kilometers, a mass of the same as the mass of the sun, roughly, a density at the center of about 10 times the density of an atomic nucleus. So these stars are essentially gigantic atomic nuclei in some sense. and they orbit around each other, spiral together as they emit gravitational waves, collide, and produce a fireball that will emit every form of electromagnetic wave that astronomers have ever seen, so not just gravitational waves. That is one of the strongest sources, and the other is binary black holes. So this is a binary black hole as seen from the bulk. The two black holes, and these are funnels in the bulk, you recall that phrase. And these are the black holes in-spiraling toward each other as they emit gravitational waves, merging, emitting a huge burst of gravitational waves in the merger, and then ringing down like a bell ringing down. And my personal view in 1992 was this, that these binary black holes will typically be 10 times heavier than the binary neutron stars. So we'll see them 10 times farther into the universe. And the volume over which they will be seen then is 10 cubed times greater, 1,000 times greater than for the binary neutron stars, since there are 3 dimensions of space. And I thought that this was very likely to outweigh the rarity of black holes compared to neutron stars in the universe. So the first things LIGO would see would be binary black holes, and would see many more binary black holes than binary neutron stars. I was right, but almost all of my colleagues disagreed. They were all expecting to see binary neutron stars. I think basically because we knew more about binary neutron stars than black holes, and they were not willing to accept arguments like this. Another key point was that when analyzing LIGO's data, it's crucial to know then the gravitational waveforms from these binary black holes in order to be able to compare theoretical waveforms with the observed waveforms in order to get the information out about what the black holes were doing when they produced the gravitational waves. And so I pushed very hard that we have to establish a second track of research in parallel with the work on the interferometers, developing them. And this was, as I said, beginning about 1992, an effort to compute the waveforms from the in-spiral merger and ring down of binary black holes, to compute those via computer simulations. And then there was more to my personal view in 1992. And the next piece was that if nature is unkind, then the strongest gravitational waves are going to be so weak that the mirror's quantum noise will hide the waves. What do I mean by quantum noise? Well, this is this is the same gravity wave detector as I talked about before, but a different rendering of it. These are the 4 mirrors there. This is the laser. That's the photodetector. But the key thing is that because of the effects of quantum mechanics, just as an electron inside an atom, we never know precisely where it is because of quantum effects. It just wiggles around randomly, unpredictably inside the atom, so you only know the probability for where it is. Similarly, for one of these mirrors, we don't know precisely where its center of mass is, and LIGO was built, and we spent several $100 million to guarantee that our output signal is sensitive only to the motion of the center of mass of each mirror. So each mirror is behaving like a 40-kilogram particle. We have 4 40-kilogram particles, and those particles, although they're 40 kilograms, enormously heavier than an electron, they have an uncertainty about where they are. That uncertainty is extremely tiny, far less than the size of an atom. But that uncertainty means that they are wiggling like that all the time, and you just can't control those wiggles. And so that quantum noise is going to hide the gravitational waves. And so to deal with this quantum noise, it seemed clear to me in 1992 that we had to develop a new form of technology that nowadays is called quantum precision measurement technology. It's sometimes also called quantum sensing. It is a cousin to quantum computing. And so this is a big deal. It's moving technology into the quantum domain. And this is, I think you're all aware that this is happening today. And this is what I was saying together with Vladimir Brzezinski, my Russian colleague, we had to do for LIGO. And so that was a new track 3 of research. This quantum precision measurement technology had to be going on in parallel with the computing the gravitational waveforms of black hole collisions in parallel with the main interferometer development effort as of 1992. So now a preview, nature turned out to be kind. The strongest waves did not require quantum precision measurement technology. The quantum noise was weaker than the strongest waves, but today we are measuring gravitational waves that would be hidden by quantum noise if we did not have QPM technology, and we do have it today thanks to track 3. So the plan for the remainder of my lecture is that I'm going to talk about track 2 for just a few minutes, the computation of the binary black hole waveforms in that period from 92 to 2015, with a goal of being mature enough for LIGO's first gravity wave observations before gravity waves were discovered. And then track 1, that advanced LIGO discovers gravitational waves, and then the quantum precision measurement technology that was developed and is in LIGO today and looking to the future. So track 2, computing the binary black hole waveforms. In 2001, I left day-to-day involvement in LIGO. By then, I had trained enough really brilliant theorists to take over the roles that I was playing in LIGO and do it better than I could, the younger theorists. And so I was no longer needed in LIGO, but I was needed to help make sure we got this binary black hole waveform computations going forward successfully. And so I then built together with Saul Tucholsky, a former student of mine who then was a professor at Cornell, we set up the Cornell Caltech SXS project to simulate extreme space-times, those being, initially it was simulating binary black hole, in-spiral merger, and ring down, by solving numerically on supercomputers Einstein's general relativity equations. We put together a research group of about 30 superb computational scientists. That was enormously larger than other research groups who were working on this at the time, except for one research group in Germany that was about this same size. And we chose that size because we had to be sure that by the time LIGO was ready to see its first gravitational waves, and as I said, I knew approximately how strong those waves were, and so I had some idea when we would see it. We needed to be sure that the simulations were in place by that time. And indeed, by 2013, this SXS team was able to simulate on supercomputers the in-spiral merger and collision of black holes with mass ratios 8:1. The heavy one is 8 times heavier than the light one, with spins up to 90% of the maximum spin allowed for a black hole. And that was, and we had at that point 171 simulations in hand, with 140 more underway. And this was adequate for LIGO's first gravity wave detections, 2 years, just barely 2 years before the first gravity wave was seen. So back to track 1, advanced LIGO, the discovery. 1.3 billion years ago, in a galaxy far, far away, 2 black holes circled around each other. This is what they would have looked like to your eyes with a field of stars and dust and nebulae of gas behind them. You're seeing the shadows of the horizons of the black holes orbiting each other. And they spiraled together, emitting gravitational waves, collided and merged and vibrated and produced a huge burst of gravitational waves in the late piece of the in-spiral, in the merger, and in the ring down. Those gravitational waves traveled out of the galaxy in which the black hole binary lived into intergalactic space. For 1.3 billion years, they traveled across intergalactic space until 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. This burst of gravitational waves reached the outer reaches of our Milky Way galaxy. For 50,000 years, this burst of gravitational waves traveled across our galaxy until it touched down on Earth on 14 September of 2015, touching Earth initially around the tip of the Antarctic Peninsula. We know from the observational data. That burst traveled up through the Earth and emerged to the LIGO gravitational wave detector in Livingston, Louisiana. And then 7 milliseconds later, 7/1000th of a second later, it emerged at the gravity wave detector in Hanford, Washington. So that's how we knew it, somewhere to the south, because it hit Louisiana before it hit Hanford, Washington. The 1,000-person LIGO collaboration analyzed the data for several months to be absolutely sure this was due to colliding black holes and to understand the details of the source. And we announced the result on the 12th of February in 2016. It made front page headlines in all the major newspapers around the world. This is in Vienna, almost all of the front page taken up by this story. New York Times, the photograph, and with a faint chirp, scientists prove Einstein was correct, a ripple in space-time. And what was it that we saw? By comparing the cleaned up signal with the theoretical waveforms from the computer simulations of the SXS collaboration, it was inferred that I keep saying we, I should emphasize that I was no longer involved in the day-to-day operations here. So it was the younger generation who had taken over from me, and Ray Weiss and Barry Barish, who were still involved, but I was not. So they, my successors, saw inferred that this was 2 black holes, 29 and 36 solar masses, for a total of 65 solar masses, collided and emerged, and the final black hole was 62 solar masses. So it is as though 3 suns had been annihilated. All of the mass in those 3 suns had been converted into gravitational wave energy, traveling out, and this happened in a time of a fraction of a second. And for just knowing that much, we could infer that the total power output during that merger was 50 times larger than the total power that comes out in light from all the stars in the observable universe put together. 50 universe luminosities in a fraction of a second, 3 solar masses of gravity wave energy into gravitational waves at a distance of 1.3 billion light years. This is a movie showing what that collision looked like as seen from the bulk. You see 2 funnels in the bulk, as I described before, and this is just before the collision. The color coding is the slowing of time near the horizon of the black hole. Where you see black down inside there is inside the horizon. And this is gone into slow motion. And there's a gigantic splash in the shape of space, and then an oscillation of the shape of space and the rate of flow of time as the burst of gravitational waves goes traveling out into the universe, carrying the information that we got from LIGO. August 2017, 2 years later, a team of scientists in Europe called the Virgo Collaboration has finally gotten their gravity wave detector working quite well. They've built a similar gravity wave detector to LIGO. This is a project of 19 laboratories, 250 plus scientists from France, Italy, Netherlands, Poland, and Hungary. And on the August 14th, 2017, that's how these names of these events go. This is the year, that's the month, that's the day. A burst of gravitational waves came in and was seen by the Virgo detector plus the 2 LIGO detectors. With 3 detectors, it was possible to triangulate on the sky from just the delay in arrival time of the signal and see where, in 2 dimensions on the sky, see where the source was. And the source was in this little error box on the sky. Whereas all previous signals, all we knew was where it was in these two dimensions, not in the third dimension. We needed that third detector to see it in the third dimension. And then just 3 days after that signal came in, we got a signal from the collision of two neutron stars. These neutron stars orbit around each other, spiraling together, and emitting gravitational waves as they spiraled in. They collided, produced a fireball that emitted all forms of electromagnetic waves that astronomers can see, and that fireball is called, and the explosion is called a kilonova. And from the gravitational wave signal, this is the signal as a function of, the frequency of the gravitational waves is a function of time, peaking up. Here's when the merger occurred. 1.7 seconds after the gravity wave signal merger waves arrived, a burst of gamma rays arrived. Very high energy electromagnetic waves. LIGO and Virgo told us that the source was in this tiny region on the sky. The Fermi Gamma Ray telescope told us that the gamma rays came from in here. Then in the next few hours and days, X-rays, ultraviolet, optical, infrared radio waves came in. Something like 20% of all of the astronomers in the world participated in these observations. It was really, I think, the most exciting observation that we have seen, certainly astronomically in my lifetime. And from the observational data, it was possible to discover a number of things. One was that it's very likely that most and perhaps all of the gold and platinum on Earth and in the universe is created in these collisions of neutron stars. Track 3, nearing the end, quantum precision measurement. Although we did not need quantum precision measurement for the first detections, we have needed it and used it since 2019 in a simplified form, something called squeezed vacuum. I won't go into the meaning of that. And since 2023 in full form, something called frequency-dependent squeezed vacuum. This is the new quantum technology that had to be developed in order for LIGO to keep moving in the face of quantum noise. These concepts of squeezing the vacuum and frequency-dependent squeezing the vacuum were conceived by a student of mine. My students, some of them were a lot smarter than I am. Carleton Caves in 1981 conceived the idea, not the technology for doing this, just what had to be done. And so it was Jeff Kimball down the hall from us who invented the technology. Again, buzzwords: degenerate parametric down conversion in a nonlinear crystal for physicists in the audience as a means of doing this squeezing and then sending it through a filter cavity with appropriately designed parameters for doing the frequency-dependent squeezing. But the technology then had to be perfected and made robust, and that required 1994 to 2022. It was done by the LIGO team, a huge effort within the LIGO team to bring this technology up to the point that it could do the job we needed. And that technology is now enabling LIGO to see several black hole collisions each week. LIGO has now seen about 300 black hole collisions, and it's exploring the laws that govern black holes and the properties and populations of black holes in our universe. And it has seen several collisions of neutron stars, but just the one that was close enough for the electromagnetic astronomers to see the electromagnetic waves. The others were too far away. Gravitational waves were ever so much stronger than the electromagnetic waves. Several black holes swallowing neutron stars. Again, just the gravitational waves. If they were closer, then we might have seen electromagnetic waves as well. So LIGO is now exploring the warped side of our universe with gravitational waves, and it's testing Einstein's general relativity in unprecedented ways with unprecedented precision. I want to just highlight a couple of things that we've learned. There was a signal came in on October 11th of last year. The distance of this pair of black holes is 700 million light years. That is, as these things go, very close, believe it or not. We haven't seen anything much closer than that. And the big black hole is 20 solar masses, spinning very rapidly, 78% of the maximum allowed spin, and allowed by the laws of general relativity. And the small black hole, 6 solar masses, and the spin of the big black hole is tilted off here at an angle of 30 degrees. It's really a weird and fascinating system. This is an artist's conception of what was going on with the small black hole orbiting the large black hole. And from just the properties of this, it's possible to infer that this big black hole, it was not created by the implosion of a star. It was created by the collisions of 2 smaller black holes, a 14 solar mass black hole collided with a 7 solar mass black hole to produce that guy. A long time ago, we don't know when, but that was the actual origin here. There's a test of Stephen Hawking's second law of black hole mechanics. What that law says is the following. Let's take 2 black holes that are orbiting each other, measure the surface area of the horizon of this black hole and the surface area of the horizon of that black hole and add them together and call that the initial area. Then that initial area has to always be, Stephen Hawking told us, smaller than the surface area of the final black hole after the merger has occurred and the ring down is finished. And he also has told us that this is demanded by the laws of quantum physics, that there is a deep, deep connection through quantum physics between the areas of black holes, and that this is really basically the second law of thermodynamics for black holes in disguise. So it's really a highly important for theoretical physics prediction of Stephen Hawking. Okay, January 14 of this year, a signal comes in, just an ideal signal, enormous signal-to-noise ratio of 80 in amplitude. Square that for the power signal-to-noise ratio. From the in-spiral waves, was it possible to infer the sum of the surface areas of the initial black holes? From the ring-down waves, I'm not paying attention to the merger waves, but from the ring-down waves, it's possible to break them up into and show that they are the sum of 2 modes of vibration of the black holes, 2 tones, think of them as that, as in music, 2 tones. There's the fundamental tone, and then there's the overtone. And from each tone, from the properties of each tone, it was possible to infer the final mass of the black hole and the mass of the final black hole and its spin and its surface area. And those agreed to within the accuracy of the measurements. Quite remarkable. They had to agree according to the laws of black hole physics that Stephen Hawking was largely responsible for. And then it was possible to make a plot then. This is a probability distribution for what is the probability that you have the final area minus the initial area divided by the initial area. This is what Hawking told us had to be positive. And here's a tiny tail in the probability distribution that is negative. There's a tiny, tiny probability that Hawking was wrong. What is that probability? You just measure that tiny tail. It's less than 1 in a million. So probability that Stephen Hawking was wrong, less than 1 in a million. Experimental result. I mean, it just warms my heart as a theoretical physicist. By the 2030s, we hope, if Congress willing to fund it, we expect to have a 40-kilometer successor to LIGO beginning to go into operation. It's called Cosmic Explorer, and a similar new, much larger gravitational wave detector in Europe. And we'll also have, by the 2030s, 3 other types of gravitational wave detectors operating 3 frequency bands. We'll have the ground-based interferometers, LIGO, and Cosmic Explorer and Einstein Telescope, looking at gravitational waves with periods of milliseconds. We'll have LISA, 3 spacecraft that track each other with laser beams, and they move relative to each other under the action of a gravitational wave. And this will tell us about gravitational waves with periods of minutes to hours. Pulsar timing arrays. You look at the pulsars, which are sources of radio waves that pulse very, very regularly, very precise timing between the pulses. And when a gravitational wave sweeps over the Earth, it causes the rates of clocks on Earth, in some sense, to speed up and slow down. And so you see a slowing down and speeding up of these pulsars in a particular pattern. That has been already seen. And so we are seeing, through these pulsar timing arrays, gravitational waves with periods of years to decades, very probably from the in-spiral, superposition of the in-spiral motion of gigantic binary black holes, hundreds of millions to billions of solar mass black holes. And we will have also a technique called CMB polarization that I'll mention right at the very end, looking at gravitational waves with periods of hundreds of millions of years. The gravitational waves that came from the Big Bang. And so this is my very last, very quick topic, exploring the birth of our universe with gravitational waves. Physicists' current best guess of how our universe was born is that it was born in a Big Bang singularity. Singularity meaning a place where the laws of physics as we know them fail, and probably new laws of quantum gravity take over that we don't understand very well. That Big Bang singularity, according to this best guess of how our universe was born, produced nothing but quantum noise, the minimum amount of fluctuations of every fundamental particle that is allowed by the laws of physics. But the very least amount of these particles that quantum physics allows. And the Big Bang injected this quantum noise into our universe's space, which, under this theory, was inflating. It was expanding exponentially fast, extremely fast expansion. And this quantum noise, these particles flashing in and out of existence, the minimum amount of particles, fed off of the energy of inflation of space to produce all the matter and radiation that we see in our universe today, and even produce the fluctuations in the density of matter that gave rise to the clusters of galaxies that we see in our universe today, according to this theory. And the numbers work out pretty much just right to explain then the sizes of clusters of galaxies and their distribution in the universe. But a key piece of this is that this also produced primordial gravitational waves. Tiny fluctuations of the minimum amount of gravitational waves amplified then by sucking energy out of the expansion produced primordial gravitational waves strong enough to be observed. Now I speculate that this beautifully simple theory will be proved wrong in the coming few decades by observations of primordial gravitational waves. Why do I speculate that? Because I have had the experience of our physicists' hubris of thinking we really understand how the universe works. And then the universe gives us a huge surprise and we're wrong. And what we thought was so beautiful, it had to be true, but we were wrong. What the truth was something that was different, and we're now struggling to figure out why is that so beautiful. So I'm really struck by the false hubris of theoretical physicists, and this is one place where I think there's a good possibility that we're wrong. I hope we're wrong, because that will produce a real revolution in our understanding of the universe. And so the primordial gravitational waves produced by inflation, working off of the quantum noise from the Big Bang, traveled out through the universe. And at age 380,000, we know that that is the time when the hot matter from the Big Bang is cooling off enough that it is starting to recombine. The electrons are being swallowed up by the protons to make neutral hydrogen, and no longer are these electrons scattering electromagnetic waves. And for the first time, electromagnetic waves are able to propagate freely. And those electromagnetic waves that are liberated so they can propagate freely are microwaves today, so this is called the cosmic microwave background. And the gravitational waves interacting with this cosmic microwave background while it is being created, according to theory, which is reliable theory, place on it an imprint called the polarization imprint that is a unique imprint that we hope to be able to observe cleanly, I think, by the end of this decade. I'm quite hopeful. And it will tell us about primordial gravitational waves whose periods today are hundreds of millions of years. These study of polarization of the microwaves from the Big Bang. And the spectrum of those waves will be a convolution, a combination of the effects of the inflation and whatever came off the Big Bang. Whatever came off the Big Bang is controlled by the laws of quantum gravity. So we want to simultaneously understand the laws of quantum gravity and how the universe was born. And this has that information in it, mixed up with the effects of inflation. Around 2050, maybe 2060, I expect that there will be a successor to this LISA mission. It'll be a combination of a number of spacecraft that track each other by laser beams that will be observing directly the gravitational waves with primordial gravitational waves of periods of seconds. Again, the wave spectrum will be a convolution of whatever came off the Big Bang with inflation. If the gravitational wave spectra and the statistical correlations in those gravitational waves in these two frequency bands, two gravitational wave period bands, hundreds of millions of years and seconds, enormous difference between those. If those spectra and statistical correlations disagree with the theory of inflation, then we will have on our hands a revolution in our understanding of the birth of the universe. And this is what I think there's a very good possibility will happen and what I am looking forward eagerly for. So just to conclude, we are just at the beginning of gravitational wave and multi-messenger astronomy, multi-messenger combined electromagnetic and gravitational. And I believe that, I'm convinced that gravitational wave astronomy and multi-messenger astronomy together will revolutionize our understanding of the universe by the end of this century and beyond. Thank you.